profesor Flavio Cavanna do FGW, dos maiores expertos de física experimental do neutrinos do mundo. É dos líderes do... É verdade, é dos líderes do programa do FGW, programa dirigido por os neutrinos. Aproveiten dessa aula, aproveitam para fazer perguntas, porque dá para entender muitas coisas. Ok? Boa aula.
Okay, so in spite of the fact that the title and the first slide is in Portuguese, I'm not going to make any other effort except this, so I will follow in English. So good afternoon, everybody. I'm very pleased to be here in Campinas again. I've been here 6 months ago, and it's a really big pleasure for me to come over again and to meet students here for in these 2 occasions that we will have to stay together for a couple of hours or maybe a little bit more. Okay, so the idea of I have 2 lectures that I prepared for this occasion. The first one is essentially concentrated, as Ettore said, in exploring various ways in which neutrino interact with matter and how detector can be built to exploit the feature of this interaction to give us indication about the nature of the difference. In this first slide, there are 2 neutrino interaction events that you can see. Neutrino, in this case, this is an image. We will be at the end of these 2 lectures, you will know a lot of details of how these images are essentially obtained out of neutrino interactions. Just to anticipate what will be clear later on, in this case we have a neutrino that is a neutral particle carrying spin half, a very, very tiny mass. Interact with nuclei, in this case of argon, producing these type of events, where here 2 protons are detected, emitted in a back-to-back configuration, and the muon carrying the flavor of the neutrino that interacted originally, which was a muon neutrino. And here there is also another event, simpler than this, with only 1 proton and another longer track representing the muon that is emitted. Okay, so this is just to introduce the topic of today, but in a better way, and here, outlining what will be the discussion that we will carry on for the rest of the day. So I will go through sort of a tour of what are the sources, the available sources for neutrinos that are currently exploited for neutrino physics, and subdivided into energy range that these neutrino come. Then I will talk into, depending on the energy range, I will focus on what are the actual interaction mechanisms that occur in those specific energies and how the neutrino interact, namely what are the cross-section, so the physics of the interaction between neutrino and the target mass. I will talk also specifically, where possible, of how the spectra of these neutrino are distributed over the energy range that I will characterize the neutrino source, and what are the experiments that use this mechanism, this cross-section, and this spectra to derive the neutrino properties, which are essentially the main resultant achievement. Once that will be done, I will focus more on what is the current development of the neutrino physics today and tomorrow, based on what is the currently known worldwide neutrino program that is being launched in the US. At the base of this program, there is a technology choice that is the one that is corresponding to the liquid argon time projection chamber, which provided the images that I mentioned, that I showed you in the first slide, and which will be the topic that will be covered tomorrow, and also perspectives of this program. Okay, I did not mention so far, but anytime you want to interrupt me for questions, things that are not clear, curiosity, whatever, you do it, okay? Right, so, a guided tour into neutrino land. I tried here to classify the neutrino sources, as I said before. Where are the neutrino coming from? The neutrino that we use to produce neutrino physics. Don't know why that's happened. Okay, so let's see. Neutrinos, at least the neutrino that we use so far, and we are using so far for neutrino physics, can be classified into two major types. The natural sources, neutrinos, and the artificial neutrinos. Artificial means that we built machines that produce these neutrinos. Okay, so neutrino intrinsically obviously are the same, but the origin of those are either naturally produced or artificially produced by machine that we built. So what are the natural sources of neutrinos that we use? The sun, which is the most abundant one. Supernovae, so neutrino coming from supernova explosions, may occur, and may occur that the propagation of these neutrino emitted at that in this very explosive event of the supernova collapse may reach us. Atmospheric neutrinos, those which are generated essentially by cosmic rays impinging upon the top level of the atmosphere and then producing neutrinos that reach us on ground. And these are the natural sources of neutrinos. On the other side, we have artificial sources which are from reactors. So energy plants that based on fission processes produce neutrinos, very abundant source of neutrinos. And from accelerators. These are dedicated machines that we built in order to generate neutrinos for our studies. I discovered that, in moving through computer to another one, I lost the font. This is not NE, but is N, you should read neutrino, okay? So these are the type of neutrinos that are produced by these sources. So the sun essentially produces only electron neutrinos. I'm sure you know that there are three types of neutrino which are associated with the corresponding charged leptons. So there are electrons, muons, and taus, and correspondingly there are neutrino E, neutrino mu, neutrino tau. So the sun generates a large flux of electron neutrinos, while from supernova explosions, all type of neutrino, E, mu, and tau, are all generated at the same time. Atmospheric neutrinos are essentially a mixture of electron and muon neutrinos. Very rarely can reach the energy to produce tau neutrinos. Very, very rarely. So, reactor neutrinos are producing anti-nu-E, so you know that neutrinos are accompanied by the anti-particle, which is called anti-neutrino. Each one, for each species, there are, electron, muon, neutrinos, and electron, muon, and tau antineutrinos. Accelerator neutrinos okay, here let me say one thing on this side. Accelerator neutrinos I subdivided this source into two sub-sources, say. One is, the color here is not very good, nice to read, but it's beam dump, and I will explain later what beam dump means, in short and long baseline accelerated neutrinos. So this is a subdivision between high energy or lower energy type of neutrinos. In this case, essentially the neutrinos that are produced by accelerator for short and long baseline studies are essentially muon neutrinos with a very little contamination of electron neutrinos. While in the beam dump accelerator generated neutrinos, there are both nu mu and nu e of both sign. And for each of these column here, there is the corresponding energy range. That is the one that we have to focus on for the further discussion. And as you can see, for instance, the sun produces neutrinos which are covering the range between 100 keV and a bit more than 10 MeV, 20 MeV essentially. Okay, so these are in the lower portion of the energy scale that we explore, or that we explore so far. For instance, supernova neutrinos are partially overlapping with the solar neutrinos, but may extend toward, the supernova, I got confused here. The supernova is the green line, covers partially the solar neutrino, but moves in the range between 10 and 100 MeV. The reactor neutrinos are instead almost overlapping with the solar neutrinos, actually from 2 MeV to 10 MeV or so. Also, the beam dump experiment cover essentially the range of the supernova neutrinos, in the range of tens of MeV. These are essentially the low energy neutrinos, what we call the low energy neutrinos. And correspondingly, there are the high energy neutrinos, which are essentially covered by the atmospheric neutrinos that go from 100 MeV up to very high, can be extended further on. But essentially, the experiments are sensitive, that we collected so far are sensitive to the energy up to 100 GeV. So we are, and take into account that we move from 100 keV and now we are talking about 100 GeV. Okay, so we are now 6 orders of magnitude, towards higher energies. And similarly for the accelerator neutrinos, we cover a range that is also in the high energy range between some 100 of MeV up to say tens of GeV. This is just to guide your attention over the spread of the available sources of neutrinos, which, as I said, cover in these covers at least 6, 7, 8 orders of magnitude. Clearly, over this large range of energies, very different type of interaction can occur. Okay, so imagine, to move from the MeV range to the 100 of GeV range. Clearly, the mechanism that the neutrino can undergo in interacting with matter are totally different. And this is the reason why I will go through one by one, try to focus on each specific range of energy and the corresponding type of interaction that can occur. And later on, see how this interaction can be detected and recorded, and how one can extract information for these neutrinos and the origin of those through the collection of the information that the detector can provide, exploring this energy range. Color also here is not very good, but what I just mentioned, however, is not the whole story. So the 6, 7 order of magnitude that I mentioned before is just a tiny portion of where other neutrino can be produced and potentially be available for detection. You see here we are in the range of micro electron volt to the energy of EeV, which I don't even know what E stands for, which is 10 to 18 electron volt. So we go from 10 to the minus 6 to 10 to 18. So there are 24 order of magnitudes in this scale. And neutrinos of different sources can cover the whole range. The one that I mentioned in the previous slide is just this portion here that you barely may see in this box here. Okay? But there are neutrinos which are at much higher energy, as well as neutrinos which are at much lower energies. Unfortunately, so far, we are sensitive, we have been sensitive to detection of this portion of the energy spectrum of neutrinos, but we still don't have collected events in this range, neither in this other range. So, a little bit of history. Neutrinos, as you know, have been, the neutrino hypothesis comes from the early 30s, Pauli hypothesis, but it took 20 years, 26 years, before the actual discovery of the existence of the neutrino, which occurred in the middle of the 50s, using neutrinos from the reactors. So reactors neutrinos were the first to be observed. That confirmed the hypothesis given 26 years before, based on observation from Fermi and the hypothesis launched by Pauli. Later on, just after the initial discovery, neutrinos from the sun, which have, as you remember, same or share essentially the same energy range, have been observed. Then, later on, by the end of the 60s, neutrinos from atmosphere, the so-called atmospheric neutrinos, were also observed on Earth. Then that started the era of the neutrinos from accelerator. And so the first created and detected neutrinos in a bubble chamber, as the image here shows, were in the, essentially this was end of 60s. Then we had a very lucky and so far only detection of neutrino from supernova, which occurred in 1987. And this is one of the major events in the history of science, I'll tell you. And we will go through this a little bit more into detail in a few minutes. Oh, once again. Then there are neutrinos from the Earth. I will not talk about this, but these are also being detected. These are decays of radioactive component in the Earth crust that have been detected in the early 2000s. Then, this slide from a friend of mine was done a few years ago, and later in 2012, the neutrino from galactic sources have been observed. Not yet, but closely, and soon after, they have been actually detected. Finally, just to mention, neutrinos from the Big Bang are a big challenge, and we are not even close to be ready to detect them. But we should, and that would be a fantastic achievement if one day one can reach that. This is what it says in this slide. So the lowest energy of neutrinos in the range of the sub-electron volt, milli-electron volt or lower, are the so-called relic neutrinos, or cosmic neutrino background, whose symbol is this one, C nu B, which is similar to the CMB, the cosmic microwave background. The origin of these two, is the same, is when neutrinos in the early stage of the universe decoupled from the rest of the matter and started traveling freely across the universe's formation. Similarly happened later for the photons, for the cosmic microwave background, which are photons that decouple later on in the evolution of the universe. Photons decouple some minutes after the Big Bang, while neutrinos decoupled much earlier, seconds, 2 seconds after the Big Bang. So they may carry a lot of information of the birth of the universe if one can detect them. Unfortunately, as we said in the previous slides, we are not even close to that goal. But it would be extremely fascinating to get them. And the number of neutrinos in the universe is very large. There are 100 neutrinos per cubic centimeter of each flavor surrounding us and distributed across the entire universe. But they are extremely difficult to detect because their energy is so little, so low, that it's very difficult to even imagine a mechanism that allows us to detect them. However, there is maybe one hope to do so. There is this reaction, helium-3, H3 plus neutrinos, which produces helium-3 plus an electron. This type of reaction has essentially no threshold. So this neutrino here, to interact with this object, may carry almost zero energy to induce this reaction. This reaction, however, emits an electron, which will be a very low energy electron though. But the electrons are visible, are charged particles. And there is the hope that this electron may be one day detected in specific detectors. So having a detector based on use of this tritium target exposed to the neutrino cosmic background may lead one day to the detection of these electrons and the proof that these neutrinos do exist. Yes?
Flavio, what's the energy of that electron?
What is the energy?
The spectrum of the electron.
Will be in the milli-electron volt. So below milli-electron volt. So it will be really difficult to probe and to detect these electrons in Cavanna detectors. But this is helpful for this purpose. This is the extremely low energy range. What about the extremely high energy, the extreme high energy range on the other side? Well, I mean, there are neutrinos which are, these neutrinos are those which are in the range above tens or hundreds of TeV, in the range of the PeV, which is 10 to the 15 electron volt. So, I mean, these neutrinos are very rare. They may be produced by catastrophic events in the universe, like neutron star formation or formation of black holes. These are very high energy neutrinos, but when produced, these neutrinos may even be increasing their energy, reaching the ultra high energy range above this level of energies through the interaction of these high energy range, very high energy neutrinos with the cosmic microwave background, and reaching more. There are mechanisms that allows neutrino to increase and increase and increase their energy. And so, if one of these neutrinos reach Earth, we may detect it. The problem is that it will be very rare. And indeed, in the South Pole, there is a large detector called Ice Cube, and this is a picture of one of these neutrino events in the range of this range, of the very high energy range. Indeed, of these type of events, there are expected to be one event per year per square kilometer of a detector. This detector covers several square kilometers of surface. And the detector is buried under the ice of the South Pole. But if you want to go to these neutrinos, they are expected to be produced at the rate, to reach the Earth at the rate of 1 percentile per square kilometer. So, I mean, either we wait for 100 years to see one, or we have to create humongous detectors in surface to have the hope to catch one very rare. So these are very challenging from the experimental point of view, but the possibility to do so is, is not too far away on our path. Actually, I mean, a detector of this size already exists and takes data. So what happens now to the neutrinos? We said at the beginning, covering this very large spectrum of energies, neutrino may undergo very different type of interaction while they cross the matter, and in particular the matter that compose the detector, because this is the way in which normally neutrinos are detected. So you use a block of matter with some, with some detector that's look into this block of matter and extract the information of what happens inside the block of matter. So this block of matter represents the target for neutrinos, but at the same time is the active element of the detector itself. So this is the technique that is currently used for neutrino experiment at all energy, I would say. So, but we were saying about what type of interaction do occur for neutrinos moving from lower to higher energies. Well, I mean, neutrino carry energy, and therefore they have a associated wavelength, if you want, quantum wavelength. So according to to what is the energy carried by the neutrino can in turn through this through its wavelength see the target under various resolution power. So if you have a long wavelength, means low energy, the target will appear as a point-like target point. If you increase the wavelength and therefore the energy, this will become, at some point, the target, increasing the energy, will become visible at its actual size. So it will be not anymore a point-like target, but it will be a target with an extension. And then increasing more and more the energy, you can start to look into what this target contains. So substructure inside the initial target structure. And if you increase more and more, you are sensitive to more details of what happens inside the structure. So reducing the wavelength, increase the momentum transfer, higher space resolution, and you probe more inside the target. Okay, so that's the method. So low energy neutrinos will see the target as a point-like target. If you increase the energy, you will start looking inside the target and being sensitive to the inner structure of the target more and more efficiently. This is shown, a little bit more into this cartoon, where, for example, a 100 keV neutrino with a very long wavelength here. You see here, this is the low energy range for solar neutrinos, so the lower side of the explored energy range of neutrinos. You see the target is the atom. So the atom with the nucleus and the electrons around it, and you see it as a whole. You're not sensitive to what is inside the atom. You see the atom as a point-like source, essentially, of interaction. Then if you increase the energy, for instance, to move from 100 keV to 10 MeV, okay? Here you see, you start to be sensitive to the nucleus, to see the nucleus inside the atom, and interacting on the nucleus as a whole. But you can do more if you go at the range of, for instance, at the GeV range. At this level, the nucleus start to become, visible in the components of the nucleus itself. So the nucleus or the cluster of nucleons inside the nucleus. And very recently, this is the image that I started with at the beginning in our first slide. This is a current, very recent result in which these two tracks, back-to-back tracks, or proton tracks, are the remnant of an interaction of a nucleon-nucleon pair inside the nucleus, which has been detected by neutrinos and shown in a very, very, very clear way. Then if you move, for instance, in the range of tens of GeV, you start to become sensitive to the quark structure inside the nucleus. So you see from the atom as a whole, electrons, nucleus, nucleons, and nuclear cluster into the quarks level. So this is the way in which the neutrino energy, increasing neutrino energy, allows you to probe more and more the structure of the matter that interact with. Okay, so this is the premise for the discussion that we have now. So I will start now for exploring into more detail the low energy range for neutrino interaction and the result of this interaction into the experiment that detected them. And we will cover the solar neutrinos, the reactor neutrinos, supernova neutrinos, and the beam down neutrinos, which are all those which are in the lower energy side of the first slide that we discussed. So, at the beginning, in the range of, say, 1 MeV or 100 keV, essentially the interaction occurs on the atomic electrons. And this is a very well-known mechanism. This is a Feynman graph that you can calculate at whatever order you want with extreme precision, with extreme precision thanks to the standard model. So the elastic scattering, on electrons essentially kicks out an electron from the atomic shell and produces an electron moving through the target, which becomes then visible into our detector. I'm not going to talk about the coherent scattering of nuclei. This is something that has been is under investigation. It will bring us into a discussion that I think we can take for questions. If we increase the energy above the few or some MeV range, as we saw before, the neutrinos start at this energy to be sensitive to probe the nucleus inside the atom. Okay, so and there are a lot of different nuclei that can be used as a target in our detectors. And these very complicated graphs here represent the cross-section, which is essentially a measure of the probability of interaction of the neutrinos with this specific nucleus. And these are, for instance, we have carbon, oxygen, argon, lead. So you can see here we have, for instance, this one is lead. So apparently lead is one of the preferred nuclear targets for neutrino interaction because it shows the highest cross-section. There are, however, other elements which have lower cross-section but a lower threshold as well. So they may be of interest to maybe prefer to use as a target mass some material which provide sensitivity to the lower range, even though with a lower cross-section, rather than having a higher cross-section. And I will tell you in the next slide why there is a threshold. So let me go back here for 1 second. You see here this IBD, inverse beta decay, which is, I think, this curve here. That is the one that has the lowest threshold among the other. And this is why this inverse beta decay that I will tell you more about is one of the preferred mechanisms for detecting neutrino interaction. To remind something in this plot, we have also these neutrinos interaction on electron. These are the cross-section here, which are lower than the nuclear cross-section. So the scattering over electrons has a lower cross-section than the scatter on the nucleus. And And these are also going down in threshold, so they are dominant in this range below that we mentioned before, below 1 MeV. So these processes, the elastic scattering on electrons, are efficiently used to detect neutrino at very low energies, while, for instance, detectors based on this reaction or any of these reactions are sensitive to neutrinos of higher energies, still in the low energy range that we talked about before. This is a summary of the main things that I just mentioned. So there is the inverse beta decay. So inverse beta decay is a charge carrying process induced by antineutrinos interacting on proton. Why is this called inverse beta decay? Because essentially, if you take, let's see, if you take this guy, this electron, and you bring the other side of the arrow, and you change the sign, what that will be is the neutron decay. Okay, so is the current, best known beta decay that has been detected in the 30s. Okay, so the neutron naturally decay into a proton, an antineutrino, and an electron. The inverse of this reaction is when the electron is on the other side, and these are those which interact. Okay, so antineutrino interacting on protons. So if you have a material that is rich of protons, what is a material that is rich on protons? Any hydrocarbon, so any hydrocarbon can be used as a target, because hydrocarbons are essentially a carbon surrounded by a number of hydrogen atoms, or protons, which are essentially bound very lightly to the carbon, so they are essentially free protons, free proton target. So if you have, and this is what the liquid scintillators, so scintillators, are usually made of. Okay, so this is what one may use for building up a detector, liquid scintillator or plastic scintillator if you want, or in the water, H2O. So there are two hydrogens and one oxygen, and the two hydrogens are the free proton, almost free protons that are the target for this reaction. So water is cheap, scintillator is relatively cheap, and it provides a very good target for neutrino interaction, especially in the lower energy, because the threshold for this reaction is relatively low, as we saw in this plot here. So this is the inverse beta decay. It's cut here, but it goes down here. So all down few 100 keV is the threshold of this reaction. And this is why all large size neutrino detectors are essentially based on the use of water or liquid scintillator. And they use essentially this reaction. How one can detect this reaction if that occurs? So if a flux of antineutrinos go through a detector made by free proton, either in water or liquid scintillator, so the antineutrino makes the interactions here, and as it says here, converts this proton into a neutron that then starts going around, making a lot of scatters, elastic scatters, until essentially it degrades in energy and is captured, and then provides a delayed emission of a gamma. But we have also the electron neutrino here, the positron here, which is emitted and shortly after annihilates in the matter and produces two photons. So the signature of this event is two flash in coincident in time and a delayed gamma emission. So if you detect two flashes, two in coincidence and one delayed, this is the signature of the occurrence of this interaction. Elastic scattering we mentioned already before. They happen on the electron, but this is even though the elastic scattering reaction is very has a relatively low energy, is a relatively low cross section. However, this reaction is very much of interest because the kicked off electron from the atomic shell preserve or carries on the information of the incident direction of the neutrino. So they are emitted essentially forward in a small cone from the incident direction of the neutrino. So we can point to the source of neutrinos. So if we have, for instance, neutrinos coming from the sun, and we have a detector that can detect these electrons and see where they go. If they point in a certain direction, we can see where is the source of this neutrino. And if we see the sun behind us, that is the source that we were looking for. And prove that these neutrinos are coming from the source that we assume to be. Okay? And then there are all the other interactions that I mentioned before, essentially the absorption interaction on atomic nuclei. Okay, so let me see a little bit about what's going on here. So, solar neutrinos. Solar neutrinos, as I was saying at the beginning, essentially cover the energy range between 100 keV and 20 MeV or so. Okay, and spectra can be associated to various types of interaction that produce energy in the sun. And this is the list of the experiments that have been detecting neutrinos in the various energy ranges. So there is the gallium experiment, which is sensitive to this region here, through interaction on gallium nuclei, or through the electron scattering on scintillator water. Then there is chlorine, who is another experiment that was sensitive to this range. Actually, that was the first detector that has been sensitive to neutrinos in the 60s. And then there are, the electron, the other, more recent experiments on large scale on water, made on water, or, on deuterium, which is, heavy, obtained through heavy water. But, okay, I'm not sure I want to go into these details, but let me just say a few things here regarding the inverse beta decay, or in general, a nuclear reaction on atomic nuclei. So a neutrino that interacts on an atomic nucleus produces an electron, and a remaining nucleus where there is one neutron which is converted into a proton to balance the charge. Okay, so this electron here interacts on this object and flips the charge of one proton here, of one neutron here into a proton with charge +1, and emits an electron with charge -1. Okay, so the energy, the charge balance is preserved. Here is all nuclear physics involved in this, in understanding this type of reaction. There are reactions which are characterized by some quantum numbers, and there are more or less probable, depending whether you preserve, transition with spin flip or no spin flip, or change in parity or changing in isotopic value. The emitted electron, essentially, out of this interaction, is the difference. The electron carries an energy, which is the energy of the neutrinos, minus the energy which is needed to change this nucleus into this other nucleus. And these nuclei are different in nature, because if you change Z, you move one nucleus into another nucleus. Okay? If you change a neutron, if N changes, it doesn't matter. You remain is an isotope. But if you change Z, this is another nucleus. Okay? So, okay, here is one example of what I mean. Gallium, that I mentioned before, sensitive to very low energy, neutrinos. Gallium, into the transition that I was mentioning before, can be changed into a germanium atom, nucleus, which has Z plus 1 of it. And, but you have to pay this energy to change from here to here. So the neutrino, incoming neutrino, releases or pay this energy and emit an electron, which is the difference between the electron, the neutrino energy, and the energy to move from this state to this state, or the other states. Okay? The deuterium that I mentioned before, which is obtained through heavy water, essentially moves into the dissociation of a deuterium nucleus into 2 protons and electron with a very little threshold of 1.4 MeV. And so this is why it's also, this one is also a very interesting target for neutrino physics. And then there is argon that we will talk about for the rest of these 2 days, which also can be used for target of low energy neutrinos in the range of the solar neutrinos, because the threshold that you have to pay here to move an argon nucleus into a potassium nucleus is 1.5 MeV. But the most probable transition is up to here because of conservation of quantum numbers. And this threshold is 4.3 MeV. So to reach from this level to this level, which is the most convenient in terms of conservation of quantum number, is a big cost of 4 about 5 MeV. So an electron neutrinos of 15 MeV produced in the sun produces a 10 MeV electron. The rest goes into balancing this energy for this to allow this transition to occur. Okay, so these are the mechanisms that can be used: electron scattering on inverse beta decay, or absorption on different target nuclei. These are the type of interaction that occur in this low energy range. Each of them can be used, of this target, can be used for detectors, for creating the mass of a detector, who, however, depending on how they are built, they can provide additional information. So one basic information is to measure the rate, so how many events per unit of time you detect. Solar neutrinos are coming from the sun day and night at an incredibly high rate of billion per square centimeter per second. Okay? Billion per square centimeter per second. If you have a simple device that counts the number of these interactions, you may expose your detectors to solar neutrinos for a year, and at the end of the year you count how many you collected. And you measure the rate, which is a fundamental number. But one can do more if you have a more sophisticated detector, which may allow you to detect this energy of the produced electron. So not just a sign that the interaction occurred, but you also detect the electron that is produced, and you measure the energy of it. So measuring the energy of the electron is very important for the reason that I mentioned in a second. You may also do measurement of the remaining nuclear part of the interaction, so detecting both the electron and the remnant nucleus, and the sum of the two will give you the total energy of the incoming neutrino. So you can reconstruct what was the incoming neutrino energy precisely. And this is what the most sophisticated detector can provide. Why I will say that, for instance, measuring the electron energy spectrum is important? Because if neutrinos are produced in the sun, in the core of the sun, at the center of the sun, and then neutrinos traverse the whole volume of the sun, reaching its surface, and then propagating through the vacuum space from the sun to the Earth. and then finally reach the detector where they are detected. They travel for a long distance, either in vacuum, in the intermediate stellar medium, which is almost vacuum, and inside the dense medium of the sun. So mechanism can occur during the flight, during the path from the point where the neutrinos are created and the point in which neutrinos are detected. And these mechanisms are what now we know are the so-called oscillation mechanism. So if an oscillation mechanism occurs, which means that the neutrino traveling across this distance changes flavor. It is born as an electron neutrino, but along its path changes nature into a muon neutrino or a tau neutrino, and disappears as an electron as it was initially as an electron neutrino. When we collect the energy spectrum of the detected electron neutrinos at Earth from the sun, we may see a distortion in the spectrum because part of these neutrinos, of the flux of neutrinos, changes, varies, oscillates, and disappears. So if we detect a spectrum variation compared to what is expected in case of unperturbed flight from the origin to the detection point, this is a smoking gun of indicating that the mechanism, like the oscillation mechanism, occurred. And since the oscillation mechanism is the only mechanism that so far has been identified as a possible indication of the massive nature of neutrinos, if we detect oscillation through the variation to the spectrum distortion of the solar neutrinos, we may indicate the neutrino have mass. And this is actually what has been happening in the recent last 50 years. Okay, so this indication of the electron energy spectrum, even more than the rate or combined with the rate, is a really fundamental aspect of the research in order to identify the intrinsic nature of neutrino, and in this case, of the massive nature of the neutrino themselves. Okay, let's move quickly to the reactor neutrinos. Reactor neutrinos, as I said at the beginning, have been the ones that we, how much time do we have? 30 minutes? Okay. I need to speed up, otherwise I will never finish. Okay, so reactor neutrinos are produced in the cycle of energy production in fission reactors, and there is a relatively large amount of energy in each individual fission process in the reactor that goes into neutrinos. So in the shape of the emitted neutrinos, essentially in the reactor you have a nuclear fission, so a massive nucleus like uranium or thorium are used for the fuel of the reactor neutrino, of the reactors, energy reactors, and then the fission occurs producing many neutrons. Essentially neutrons at some point decay, and in the decay process they produce neutrinos. And these are the neutrinos that form the spectrum of the reactor neutrinos, which are essentially distributed from 0 up to 10 MeV, which is exactly overlapping the solar, in the good fraction, overlapping the solar neutrino spectrum. These are antineutrinos because of the neutron decay gives us an antineutrino in final state. Since a fraction of the energy per fission goes into in neutrino production, energetic reactors produce a huge amount of neutrinos, an enormous flux of neutrinos, so big that near the reactor is even substantially higher, order of magnitude higher than the flux of neutrinos from the sun. So it is trillion of neutrinos per square centimeter per second near the source, near the reactor itself. And this is why Raines and Cavanna in 1956 first discovered these neutrinos, because they were using a detector positioned relatively near the reactor, and they were exposed to this very large flux of neutrino. The reaction that they used was a very efficient reaction, the inverse beta decay that I mentioned before, with the type of experimental signature that I mentioned before. So 2 coincident flash of light and 1 delayed flash of light. So if you have a liquid scintillator and the number of photomultipliers looking into this volume, if you detect a first flash of light and the second flash of light delayed within a given amount of time, this kills the background and gives you a very clean signature for detecting these neutrinos. Actually, the rate, thanks to the large flux of neutrinos produced by the reactors, was so big that one may expect to have several neutrino events per hour in a relatively small detector, like a few hundred kilograms of plastics, of liquid scintillator. So in a detector of this size, exposed to the reactor flux, one may expect to have few events per hour, thanks to this specific topology that I mentioned before, these coincidence flashes of light detected by photomultipliers. So that was the discovery of the neutrinos in the late 50s, in the second half of the 50s. Let me go then switch into the meson decay neutrino. So this is the beam dump. So we are moving now into the, already before, with the reactor or artificial neutrinos. Here we are still under, the artificial neutrino type. So these beam dump neutrinos are essentially produced by intense proton beams that are sent over a target, for instance, a water thickness. And there they interact, these protons, in the range of a GeV or so. They made interaction, produce a lot of pions. Pions decay into muons and neutrinos. And the muon in turn decays into electrons and neutrino and neutrinos. So if you send many protons, you generate essentially many neutrinos. These are neutrinos generated by pions and muons at rest. Okay, so when they slow down to the matter, this block of matter, and the spectrum of these neutrinos is shown here. They, thanks to, to the decay of the muon, of the pion into muon, and the muon into electron, and neutrino, antineutrino, E and mu, the neutrino spectra are essentially constrained up to the mass of the muon divided by 2, half the mass of the muon. So they are generated in the range between few tens, some 10 MeV and 50 MeV. These neutrinos have been detected in a detector in the 90s, for instance, in the Los Alamos laboratory in the US. And they discovered something very much unexpected. So why unexpected? Because this spectrum was it is very well known. The amount of neutrinos that are generated was also very well known, thanks to the amount of protons that was very well known. So we use artificial sources because they are controllable sources. So we know how many protons we shoot into this block of material. We know rather well and precisely how many pions per proton we obtain. And then we know how many muons, how many electrons, how many neutrinos we generate. So the spectrum and the amount of neutrinos that we expect from this experiment is very, very well known. And actually, this experiment, when looked into the rate of the detected event, showed something that was not in agreement with the expectation. There were many hypotheses that has been discussed, and the one that remains as a possible explanation is that there is a new type of neutrinos, which is not nu E, nu mu, nu tau, is another type of neutrino which can be produced, which we don't know yet whether it's true or not, because this experiment remains essentially, whether that was right or not, it remains still not demonstrated at the moment. And this is one of the major line of current development, detecting whether or not we need to have more neutrinos than the 3 that we know. These are generically known as sterile neutrinos, for some reason that maybe we will have time to discuss later on. Okay? So this big dump experiment generated hints of a possible existence of one or maybe more than one generation of new type of neutrinos. And this is a still, unanswered question that we are looking for. And big part of the program, of the worldwide neutrino program that I mentioned at some point, is concentrated in going deeper and deeper into this hypothesis and see if that will be the case. The existence of sterile neutrino may open incredibly large scenarios. Essentially, it will be a revolution into the standard model, because that will be physics out of the standard model, and it will imply a lot of rethinking of the entire understanding of physics at the moment, of particle physics, including possible explanation or part of possible explanation for dark matter, and a lot of other consequences. Let me go now to talk briefly on supernova neutrinos. I have no doubt that supernova neutrinos are the most fascinating type of neutrino that we can discuss about. So, and I will try to maybe get a flavor of why I think so. So we are here in the Milky Way, our galaxy, like billions of other galaxies around the universe, in one place somewhere right around the boundary of the Milky Way. Actually, the distance between the center of the galaxy and where we are is less than 10 kiloparsec, 8 if I remember. If there is a catastrophic event of a supernova explosion, which is the death of a star, the collapse of the final stage evolution of a star, it may occur through mechanisms which are still partially not yet completely understood, where an enormous amount of neutrinos are produced. In the collapse itself, most of the energy of the collapsing star goes in energy released under neutrinos, formed in neutrinos. So an incredibly large amount of neutrinos are emitted. So big and so large that this neutrino may travel 100 kiloparsec, and if a detector is at that distance, within that range, may still see, of course, if you expand from a point, suppose that a supernova event occurs at the center of our galaxy, while these neutrinos are emitted in this point and then start moving in a spherical wave, and of course, the more you grow the radius of the spherical wave, the less is the density of this on the surface. This goes like 1 over r squared. Okay, so the r squared is the 100 kiloparsec. So if the current detectors or the next generation detector will be sensitive to distances of 100 kiloparsec, distance where the origin of the neutrino are, and still being sensitive to detect these neutrinos, which have an incredibly low cross-section, but the amount of neutrinos is so large that even at these very large distances from the source, from the origin, may still be detectable in a sufficient number to be detectable. Okay? Now, we have only one example of detection of supernova events, which is the one that occurred in 1987. And we pointed this supernova in the Large Magellanic Cloud, which is sitting below our galaxy at a distance of 20 kiloparsec, if I'm not wrong, or so. Okay. Unfortunately, for instance, another big source of supernova are from the other large galaxy that the nearest one to us is Andromeda, but this is too far away, so we have no sensitivity at these distances. The spectrum, as I said before, is in the range of tens of MeV, so a little above the neutrino energy, but the mechanism that may occur for supernova neutrino are essentially the same. Now, the few events, 20 events that have been detected in 1997, in coincidence by a number of different detectors in the world, open essentially the way to neutrino astronomy. So we detected far point-like sources. And the information that we may extract from this distribution of few events as a function of energy, and the color refers to the different detectors that collected these events simultaneously in various parts of the world, Japan, US, Russia, are so important that all our knowledge on the mechanism occurring for a supernova explosion are extracted essentially from this plot. So all what we know at the moment on one of the most catastrophic and relevant mechanisms of occurring in our universe is known by the detection of these 20 events. How they are distributed in time and how they are distributed in energy. It's spectacular. I mean, I think that there were more than 3,000 papers, scientific papers, discussing this plot and building the foundation of the astronomical understanding of one of the most spectacular astronomical events, which is the supernova explosion. Okay, I'm not going to say anything about this. Future detectors. Okay, I mean, I don't have time to go through these kind of things. I just say that. Let me go, for instance, to what is not yet. Okay, there are several. These are the list of the detectors that are currently working, detecting possibly signal from supernova. They are observatory. They did not see anything since the last 30 years. We expect to have supernova events within 100 kiloparsec. Actually less than this, but within some tens of kiloparsec. Few per century, with a very large error in this estimate. So the last one occurred in 1987. So we are nearly 30 years after that event. So essentially, any time would be good to see a new event, if the calculation of the rate of supernova event is correct. There are several, 6, 7, 8 maybe, detectors around the world capable today to detect these signals. And new detectors are going to be built to detect these events and to extend the sensitivity to longer distances. One of these is based on argon, and this is again the liquid argon TPC that I mentioned already a few times. Mechanisms are here shown are the ones that I mentioned before, the elastic scattering and the absorption of argon nuclei, producing a potassium nucleus and an electron. These are the rate. So at 100 kiloparsec, which is here, with the future detector we will be ready to see 100 events. If we go to the Andromeda, which is at about 1,000 kiloparsec, with the future detector we will see one event. So it will be very difficult to see whether that was the real event or not. So this is why events from Andromeda cannot be essentially seen, even with the next generation type of detectors. But let me go to show you one thing here. So this is if one thing to how one can actually see with your eyes, how a supernova event can look like. Well, one can do Monte Carlo simulation, making a simulation of what your detector will look like, injecting neutrinos of a given energy in the range of the atmospheric of the supernova neutrinos, and see what the simulation of this event can tell you. But one can do even better. If you have a small detector like the one that is shown here, which is a detector of this size, the same principle, however, of operating. Certainly, this detector cannot see supernova event because it's too small. But we may see events which resemble, which are called background. Okay, so events which may be generated and recorded that look like but are not supernova event. But I'd like to show how a supernova event may look like. So you remember, maybe, this is the reaction that argon can exploit. So neutrino E from supernova interact with argon nucleus, produces at the expenses of 4.5 MeV a potassium nucleus left into an excited state, plus an energetic electron. Energetic how much? What we were saying before. So the energy of the incoming neutrinos minus the energy to move this argon into this potassium, which is 4.5 MeV. So if we have a 20 MeV electron, neutrino, from a supernova, this electron will be about 15 MeV, which is a reasonably energy to be seen in the liquid argon TPCs. Plus this object, which is a potassium into excited state. What does excited state mean? Mean that this nucleus can quickly electromagnetically decay, going down to the ground state of potassium ground state nucleus, plus the emission of gammas. Gammas can traverse the material around it and converting into Compton electron through Compton scattering. This electron, however, will have essentially the energy of this gamma nearby this energy, which will be the transition, the few MeV transition from potassium excited state to ground state, which are few MeV, 2, 3 MeV. So this object here is not the energetic electron like this one, 15 or 20 MeV, but will be 1, 2, 3 MeV or less. So this one will be seen in the TPC, in the liquid argon TPC, as a squiggle, as a short zigzagging electron track. Sort of something like that. This low energy electron from this gamma, from the excitation potassium nucleus, can instead be seen just as a spot, a little dot. Okay, so this is what one event has been seen. So there is a, if you zoom this view, you see one track here, plus two little spots. And if we make a reconstruction of these events, we see that this longer track has 13.8 MeV, and these other one have 4.5 MeV. This one is 1.8 MeV, and if you look in this bigger zoom, you see also some other that here are not really clearly visible. Okay, so this event that I show here is not a supernova event; it's a background event generated by only God knows. But this looks very similar to what we believe would be the signature of a supernova event in our detector. Okay, so looking for this signature is the goal of the big detectors that are going to be built in the next generation of neutrino detectors. Okay. Okay, so I concluded with these atmospheric neutrinos, the intermediate energy range, the low energy range. And now, maybe I can go for another 10 minutes. You want to have a break and then we start? Or no, we go until the end like this? Okay. So, and we can go into the intermediate energy range, which cover the other sources of neutrinos, which we now talk about so far, which are the atmospheric neutrinos, and the short and long baseline neutrinos. And about this will be also, the topic of what we will continue to say tomorrow. Okay? So, intermediate energy range means to cover energies above hundred of MeV, some hundred MeVs, up to several GeVs. The mechanism of interaction in this range are different, are multiple. There is this so-called quasi-elastic interaction. You remember we said at the beginning, increasing the energy of neutrinos, you see your target better and better. So instead of seeing the argon, the atomic nucleus, you start seeing what is inside the atomic nucleus. So you're sensitive to the target, into the target. So it's the nucleons inside the nuclei. And if you increase the energy at this level, you may start even be sensitive to the quark structure inside the nucleus, inside the nuclei. It all depends on the energy. So when the energy is in this range here, few GeV, you essentially are sensitive to the nucleons inside the nucleus, where neutrino may produce a quasi-elastic scattering. Quasi means what? A neutrino of flavor mu, for instance, can interact with the neutron and producing in final state a proton and a mu minus. Okay, so the flavor is preserved, the charge is preserved, and you produce, and this is a quasi-elastic in the sense that the difference between elastic and quasi-elastic is just the fact that the nucleon changes from a proton, from a neutron into a proton, so flips charge. And the neutrino becomes a muon. So flips the flavor, but not the flavor, flip the charge of the lepton from a neutral lepton into a charged lepton. And the proton, and the nucleon, from a neutron, flip into a proton. Then there are more complicated mechanisms like delta resonance, when the nucleon is brought by the neutrino interaction into an excited state of a delta resonance, and then decays producing pions. Or if you are sensitive to the quark structure, you may start in, to the deep inelastic scattering. Deep inelastic means that you probe deeply into the nucleon structure and be sensitive to the presence of quarks inside the nucleus, inside the nucleon. In this energy range, people were convinced to know very well the mechanism. They were all sort of well calculated mechanism. However, when recently, recently in the last 10 years or so, accurate, precise measurements have been performed, we discovered that there was a strange effect here, that this is the expected cross-section reconstruction, this blue dotted curve, while the measurements were very largely above it. So these are experimental measurements. These are a different model, but the current standard model prediction was this one. So this is why I call it the cross-section battlefield, because in here, to understand the reason of these disagreements, this is still a rather open question, not fully understood today. So we have, it's not a matter of going beyond the standard model, but the standard model as is not sufficient to explain all the mechanism of the neutrino interaction at the moment. We need to understand more deeply what the nuclear structure is. And when I said at the beginning that nucleons inside the nuclei may be associated in a cluster, in pairs or in a triplet, this structure inside the nucleus, which is essentially nuclear physics, may be the explanation. It is now quite clear that the difference between this cross-section and this one is because the nucleus has itself a different, a more complicated structure than a simple collection of nucleons. Okay, so nuclear physicists know that the nucleus is more complicated than just a collection of nucleons. Okay? But into the neutrino physics, we were always assuming that nuclei are just collection of nucleons. And when we do it with precise measurement, we discover that our initial picture is not valid. But it took us maybe 10 years or 15 years to understand this point, and it's not fully understood at the moment. So let's go to, where these mechanisms are active. For atmospheric neutrinos, so here is a cartoon of what happens. So there is a cosmic ray. So cosmic rays are charged particles accelerated in their travel across the universe. Most of those are generated by supernova explosions. They travel undisturbed, essentially, for galactic distances, until some of them arrived on their trajectory, cross the trajectory of the Earth, and then they go through it. So at the top level of the atmosphere, these very energetic particles, normally they are protons. The majority of the cosmic rays are energetic protons. They interact with the oxygen and nitrogen that compose the atmosphere, and they produce a cascade of particles. These are very energetic normally. So they produce pions. Pions do what I just mentioned before. They produce muons and neutrinos. And the muons decay and produce neutrinos. And these are the atmospheric neutrinos. Okay? So these are neutrinos which are generated by cosmic rays through their process of energy degradation through the atmosphere. The spectrum can be very large because the spectrum of the original cosmic rays is very large, very broad. Okay, and it goes much beyond this 10 GeV. It goes wherever. It can go to very high energies. The ones which have been exploited in experiments are, however, those which are most abundant. The spectrum falls in this way. So in the range between 100 MeV and tens of GeV is where atmospheric neutrinos have been mostly detected so far. Just to give you an idea, however, the rate of the atmospheric neutrino is, even though the rate of cosmic rays is very high, the amount of neutrinos produced by this mechanism is relatively low, in the sense that for 1 kiloton detector, 1 kiloton means 1,000 tons of active detector material. In a 1 kiloton, I think this room is maybe 1/3 of a kiloton. Okay, so you have to build a detector that is like 3 rooms of this size, one on top of the other, to make 1 kiloton of a detector. So, and to control this volume with an active mean of extracting information from what happens in these 3 rooms, one on top of the other, is not an easy game. Okay, so in a kiloton detector, we have, in a year, we have 300 events. This is the expectation. So you have to build kiloton detector to have a significant rate of 1 event per day, essentially. However, if you build a detector of this sort, 3 of these rooms, one on top of the other, full of water, of liquid scintillate, and you account how many events you see, you expect to have 1 a day, 1 per day. At the end of the year, you look at what is the rate you collected out of a year, and you will see that instead of 100, you will see 150. Where are the other 150? Well, in this path, well, actually, it's a bit more complicated than this. Atmospheric neutrinos can be produced from the cosmic ray that interact above you, but also below you in the opposite hemisphere. Neutrinos, once they are produced, they cross the entire Earth without essentially losing much of their flux. And then they may be detected into your detector that is sitting here. Well, what is surprising is that indeed, what you will see is that the number of events that you collect instead of being 300 is 150, because mostly due to those which cross the Earth from below, oscillate into another flavor through crossing this amount of material. They oscillate. They are not, interact. They are oscillating. They disappear in a flavor and appear in another flavor. And this is what led to the discovery of the neutrino oscillation. Essentially, neutrino oscillation has been discovered through the atmospheric neutrinos, and this is an original plot with transparencies made by hand. You're too young to have seen those, but some other people not, like me. So these are, the original plot in which you see the expectation from below the Earth and from above. So this is a function of angle. So from from -1 to 0, these are the outgoing neutrinos, the ones which are produced on the opposite hemisphere, cross the entire Earth, and you see coming from below your detector. The number of these was significant, was essentially half of what was foreseen. While the one from the top gave, essentially the expected number. So the reason is clear. There is an oscillation mechanism that is depending on the distance traveled by the neutrinos. And this evidence was so striking, 6.2 sigma, that immediately that led to the confirmation of the hypothesis of the neutrino oscillation. And this plot has been shown by my friend Kajita-san last year when he was, laureated Nobel Prize for this discovery. Okay, with a detector that is super kamikaze here, which contains 50,000 tons of water. So this is the great, discovery that atmospheric neutrino allowed to make. And this discovery, combined with the discovery of the oscillation from the sun, could clarify completely the picture of the neutrino oscillation, almost clarify the whole picture of the neutrino oscillation. Okay, let me go finally. Well, I'm finished, but I don't know, maybe we can stop here and we start from here tomorrow. Come on, question. 1, 2.
Preguntas, dúvidas. ¿Puede ser en portugués?
Sí, sí.
Non è credo che ninguém tenha perguntas.
Let's make a referendum. Which neutrino do you like most among the one that I mentioned? So solar neutrinos, reactor neutrinos. So solar neutrinos are led to the first neutrino, solar neutrino puzzle, the one that first show indication of possible oscillation mechanism. Reactor neutrinos is one that allowed discovery of neutrinos, and recently measuring one missing element of the oscillation matrix. So reactor neutrinos. Then what it means? Supernova neutrinos, which led to our understanding of one of the most spectacular and energetic events in our universe. Beam down neutrinos, which led to the hypothesis of the existence of sterile neutrinos, or atmospheric neutrinos, which made essentially discovery of oscillations. So who prefer what? Who is for solar? 0, not very popular. Reactor? At least 1. Let's see. Supernova? Oh, some supernova. What else do we? An atmospheric. Everybody else. Okay, so in any case, I mean, there will be a second stage of our discussion, which is the one for accelerator neutrinos produced from accelerators. So there are artificial neutrinos produced by accelerators, which are the most popular neutrino that we use normally, because we generate neutrinos in a very quite well controlled way. So we may use the information of the neutrinos that we send in to see what is the outcome of our detector, and then matching what we know about the incoming neutrinos with what we see in our detector. And one of the, if you remember, I mean, so far we said oscillation are occurring at distance and depending on the energy. So one idea of the accelerator neutrinos is to produce neutrinos and maybe putting the target, so the detector, at the far distance or at distance that changes in distance from the source, so that if there are oscillation, you may see. You may even think of having a detector position, since an oscillation that follows a sinusoidal pattern. You may even think of positioning a detector in a position where you leave the entire oscillation to occur, so that you will regenerate those which were oscillating first and see the full amount of neutrinos that you see. But the idea is to maybe have different detectors along the distance, so that you can see as a function of distance the oscillation pattern. And this is more or less what the future neutrino detector for accelerator neutrinos will be trying to see. Okay. Mm-hmm.
Pode pensar com vocês? Você mostrou uma equação lá do neutrino colidindo com o núcleo de deutério, produzindo 2 prótons e 1 elétron. Esse neutrino ele atingiu o neutro do núcleo do deutério, e a partir dele produziu os 2 prótons. E essa detecção é feita a partir dos prótons, da energia dele. É isso?
Tu metti sull'inverso di che?
L'interazione del neutrino con deuterio. È scombussolato.
Sono troppo. Cosa voleva sapere?
Se il neutrino interagiva con il neutrone.
Yes. Yeah. Yes. So neutrino interact with. Actually, it is interacting on the pair. So this is interact with the neutron and produce a.
You must have a threshold of energy to make this.
Yeah. Is one of the lowest energy that you need to create this. All the other. You see here, you have few hundred MeV. This is 1.4 MeV. But the interesting feature of this is that you may detect both the electron and the protons. So in this case, in the other interaction, you interact, you produce an electron, and you don't see the nuclei, the nucleus left in final state. You have this, you don't detect that. In this case, you detect this and also these ones. So you may sum the energy that you see for this, and calculating the energy, the overall energy, you may reconstruct the energy of the neutrinos. Instead, in the other case, you cannot, because you detect only the electron and not the recoiling nucleus.
And what kind of source came this neutrino from here?
I think these are for solar neutrinos. You see, this object here is 2 proton and 1 neutron, and these are in they essentially are in this range, which is 5 MeV threshold.
Is it an efficient way to detect neutrinos to use heavy water because of this?
Yeah. This is a very efficient, very efficient type of detection. And this is, the combination of the results from deuterium and and gallium. So comparing, let me say this thing. The solar spectrum provides neutrinos from, say, 100 keV up to 15 MeV or 20 MeV or so. Now, all these neutrinos are generated inside the core of the sun, so at the center of the sun. Traversing the dense material of the sun, the oscillation is boosted for higher energies neutrinos. So the neutrinos in this spectrum have a higher probability of oscillating. The neutrinos in this, energy range, instead do not have high probability, have a very low probability of oscillation. So if you compare the spectrum that you can see, even the rate that you can see, here you see spectral distortion and a very large suppression of rate. If you take the experiment with gallium, you are expected to see essentially the rate that you expect. So if you have an oscillation mechanism, this is exactly what you expect to see. So one portion of the spectrum not affected by oscillation, and so the rate that you calculate is comparable to the rate that you measure, while in this range you should see a rate which is consistently below what is the expected one, with a spectrum that is also very much distorted. So the combination of the deuterium experiment, as I know, and the result from the gallium experiment, the combination of these two provided a very strong confirmation of the oscillation hypothesis for the solar neutrinos.
I have 3 questions. I'm going to start with the simplest one. You showed us a graph for the scattering cross-section in terms of the energy for different materials. I could notice in there that for some of the curves you have, for one specific value of the energy, you have a range of scattering cross-sections. It was like a vertical line, and then you have to add that one. Why do you have for that specific energy such a range in the cross-section?
This is the effect of this threshold, which put a sharp cut on the cross-section. So the cross-section start is different than 0, essentially, when you compensate this threshold. Because this plot here is in neutrino energy. So neutrino energy is, if it is, let's take this one, it is more visible, okay? Which is 11 MeV, maybe, or so. So neutrinos below 11 MeV cannot induce this reaction because it's below threshold. Okay? As soon as you have just an energy above 11 MeV, the cross-section is high, and you see the cross-section appearing at this point. So it's a sharp drop because of the effect of this nuclear binding energy that is different. Essentially, this your target is gallium, and you want to go into germanium, and you have to do this to pay this energy, and this is the reason of this drop.
The second is for argon you have two channels of interaction, and one of them was the preferred one. How could you identify the percentage of neutrinos that could come from the other channel? How could you detect that?
Let me see. You mean this, for instance? Okay. So I did not discuss this into detail, but so this is the preferred transition between neutrinos, electroneutrinos, argon, producing potassium in excited state plus electron. There is a corresponding cross-section for antineutrinos, which interact with argon but produce not potassium but chlorine. So argon has Z plus 1 becomes potassium, Z minus 1 is chlorine in the Mendeleev table. So, the threshold to go from here to here is much bigger than the threshold to go from here to here. This is, I think, 4 point something MeV, 4.5 MeV. This is more than 10 MeV. So the threshold is much different between the two. If you have a supernova neutrino that can come as a neutrino E and also antineutrino E, you are expecting though that if the number of neutrino E and antineutrino E are the same, as an assumption, you will see many more of this type of reaction than this one, because the threshold is different. If you see this reaction, you have here a positron instead of an electron, and the positron may be detected as a positron rather than an electron. It's not easy. Technology did not demonstrate that it's efficient in distinguishing E plus from E minus. But if, assuming that one does, when you detect an a positron, this will only, in a case of a supernova event, this is the signature that you expect for an antineutrino. But you will detect less positron than the electron because of the threshold. Then you have also other type of reaction, which are the neutral current reaction, in which the neutrino interacts with the argon nucleus, brings the argon nucleus into an excited state, and releases a neutrino in final state. So this is a very difficult reaction to detect, because you don't have any energetic electron to see. You have only this argon in excited state, which can decay electromagnetically to ground state, emitting a photon. And then the photon converts into a Compton electron. But the Compton electron will be a low energy spot and not a track. And this will be more difficult to detect. So it's a detection issue, not a threshold issue. You know, for instance, this one is more favorable somehow than other reaction, but it will be very difficult to see or to detect.
Okay. And finally, if the existence of sterile neutrinos be confirmed, these sterile neutrinos should be included in the oscillation scheme. We should have now 4 or more neutrino oscillation or neutrinos oscillation.
Yeah. Actually, the reason why it's called sterile neutrino is because this neutrino essentially is generated, it does not interact, and may re-oscillate into a visible interacting neutrino. Okay, so the sterile neutrinos are essentially detectable only through a double oscillation step. neutrino oscillating to sterile, sterile re-oscillating to visible neutrinos. Of course, I mean, this will imply, to revise completely all the mechanism of neutrino oscillation. But beyond this is the nature of this sterile neutrino, which is totally unknown. It doesn't find any explanation or possible room in the standard model. So we have to create or to enlarge or to extend the standard model to accommodate new neutrinos. And this is a very difficult task, theoretically. And this may lead to a complete revision of the entire model that we have in mind. So it would be a big revolution if sterile neutrino really exists. Because there is no room, essentially, in the standard model for this type of neutrinos. The nature itself of these neutrinos is very much unknown. I mean, we know nothing about that, except that these sterile neutrino, under some assumption, which are not easy to explain, but under some assumption, may contribute to the dark matter budget. So they may be a component of the dark matter. So this is the only indication that we may, I don't think of other evidence for sterile neutrino. Well, it's not a direct evidence. I mean, dark matter, we know that there are very strong indication of the existence of dark matter. The nature of dark matter is unknown. Here there is another hint for the existence of a particle that may be massive, actually that will be massive, and this mass may be part of the dark matter budget.
But sterile neutrinos could be just a little part of the dark matter.
Yeah. There are a lot of models, a lot of ideas. Initially, people will say, okay, dark matter and sterile neutrinos are the same. Then it was the argument that these neutrinos, even if massive, they are too hot. I mean, too fast for being dark matter, which is essentially matter that is very doesn't move very fast, essentially. So at some point, the idea of sterile neutrino was ruled out as component of dark matter. But then there is, this warm dark matter component that may still be partially explained by sterile neutrinos. But clearly, if future generation of neutrino experiment will detect or will confirm the existence of sterile neutrino, that would be really a big earthquake in our understanding of physics, because it will require to really rethink of entire system, and it's not going to be easy.
¿Más preguntas? Vamos a agradecer.
Okay, so we'll see you tomorrow. Thank you for the attention.